Hello all of you. Welcome to the 42nd lecture on the course on analysis and modeling in chemical engineering. In the last week and this week, we are discussing graph theory applied to chemical engineering. In the last class, we discussed how we can decompose a large scale linear system containing material balance on a flow sheet, let's say, using the ideas of graph theory, and how we can determine the priority order of solving equations. So, in this lecture, I will extend the idea to a system of nonlinear equations, which need not be on a flow sheet. It can be any set of nonlinear equations that you may have for any system, not particular to material balance only, but in general, right? So, the approach follows is very similar to whatever we have done for the linear system in terms of application of the graph theory, but there is some additional language that we need to introduce in order to go forward. So, if you have, let us say, a system of equations which can be not limited to algebraic equations, it can also be differential equations and all that. So, what I am showing you here are three equations. The first one is a differential equation, the second one and third one are nonlinear algebraic equations, right? And you can imagine that you can have any kind of equations making up the list. So, in that case, I can actually make a matrix of the equations and the variables, where the equations represent the rows of the matrix. In this case, we have three equations A, B and C, and variables make up the columns of the matrix x1, x2, x3, x4 in this case, and that matrix I will refer as the occurrence matrix or the structural matrix, as I will call it occurrence matrix more often. And as the name suggests, the occurrence matrix indicates whether a given variable is present in a given equation or not. So, if it is going to be 1, if the variable is present, and it is 0, the elements are going to be 0 if it is not present. So, let us say the first equation contains x1, it does not contain x2, it contains x3 and x4. Here also we have x1 only. I am not showing a t here, probably t is known, right. So, in that case, we can have 1 for the column corresponding to x1 in the row corresponding to equation A. Then for x2, I am going to have 0. I will not put anything, means it is 0. Then x3 is 1 and x4 is 1. For the second equation, equation B, it contains x1, x2 and does not contain x3, x4. So, we have 1 in the first two column, and the third equation contains x1, x3, x4, again does not contain x2. So, I have 1, 3, 4 here. So, in general, as I said, the elements of the matrix is equal to 1 if the variable j is present in a equation I and 0 otherwise. Right? Now, clearly, in order for the set of equations to be solvable, the degree of freedom must be equal to 0. That means that the number of equations should be equal to the number of variables in order to have a solvable equation. If the number of equations are more than the set of variables, then we have like many solutions. If we have or infinitely many solutions, if I have number of equations less than the number of variables, then we have to specify some variables or we have a under specified problem, right. But for a problem to be well specified, the number of equations should be equal to the number of variables. That means that in that case, the matrix S is going to be a square matrix. Let us say if you had only 3 variables, then we have a solvable system, and in that case it would become a square matrix, right. So, we have a square occurrence matrix, means that it is a solvable system of equations. Now, for a square S, for the square matrix occurrence matrix, we can define something known as an admissible output set. And what this means is a set of elements in the occurrence matrix which basically make up the admissible output set, but there are two conditions to it. The first condition is that each equation should contain only one output element. The output elements are going to make up the output set. So, every equation should have exactly one output element, and each variable appears as the output element of exactly one equation. what this means here, right? What it actually means is like every equation, I am kind of assigning a variable to it. That means I have to solve that equation to get that variable. And once I solve that variable from that equation, I can now provide that variable to other equations, right? And that's what that's where the idea of graph will come into play, right? So let's say, for example, you have this set of equations f1, f2, f3. The occurrence matrix is going to be having the columns x1, x2, x3, and the occurrence matrix is going to be square in this case, and it is x1 1, x2 is not present in f1, all variables are present in f2, and x1 is not present in f3. And now let us say, for example, I assign that x1 is an output element of f1. So f1 will give me x1 if solved. x2 is output element of x2. So f2 will give me x2 when it is solved. And let's say x3 becomes the output element of f3, and so f3 is going to give me x3. Now what this means is, let's say f2 requires x1 and x3 in order to find x2. Where does it get x1 from? x1 will come from solution of f1. So f1 will give it x1, f3 in the same way will give it x3, because I have assigned x3 as the output element of f3. And now this f2 will compute x2 once it knows x1 and x3. And the same thing I can do it for other equations. Now clearly it is not a unique set. I can think about other possibilities. For example, we can assign, I am showing it by triangles, that I solve for, let us say, x1 from f2, and then x2 from f3, and x3 from f1, right? So I am having two sets here. One is represented by the circles, other is by the triangles. Both satisfies the two rules which I have specified, that every equation contains exactly one output element. That means along the rows you should have only one output element, and each variable appears as output element of only one equation. That means along the columns we should have exactly one output element. So both for the choices, one choice is circles, other is triangle, both make up a admissible output set, which basically satisfies the criteria whatever we have met, right? As a matter of convention, we will prefer to have output element along the diagonals of the matrix, right, which is the first set which I have mentioned. Here the ones are along the diagonals. So I will prefer to go with this, and if this is not happening, then we can do the row and column permutations in the matrix to make sure that the output element is along the diagonals, just as a matter of convention, because it will make my graph look simpler if I do that. So if it is not there, then we can do permutation. How we can do permutation? Let me start with the output elements shown as triangles. So we had f1, f2, f3, x1, x2, x3. Let us say I make a choice such that my output element is not along the diagonals. Let's say if it is not along the diagonals, right? So in that case, let us say my choice is something like this: x1 from f2, x2 from f3, and x3 from f1, right? So how do you ensure that we are going to have it along the diagonals? So we can do row permutations and we can do column permutations. So I will make the second row as the first row. I will make the third row as the second row and I will make first row as the third row. In other words, we are doing some kind of a cyclic permutation. 2 becomes the new 1, 1 becomes the new 3 and 3 becomes the new 2, right? And if I do that, it will look like this. So, F2 will come first, the row 2 becomes row 1, row 3 becomes row 2. So, F3 will come here and F1 will go there and we have X1, X2, X3 along the columns as we had, and now I am going to have the ones along the diagonal. Right. So, whenever we do not have the admissible output set along the diagonals, we can do a permutation, either row permutations or column permutations or both, in order to make it along the diagonals. Okay. Now, once we have that, then we can essentially draw a Boolean matrix using the idea that the output element of that equation basically flows from that equation to the other equations. Let us say I solve F1 for X1 and F2 for X2 and F3 for X3 in the example that I have shown earlier, then X1 basically flows from F1, where from it is solved, to F2 and F3. So, every equation therefore becomes a vertex in the graph. So, let me do the vertex F1, F2, F3, and F1 I am solving for X1 and X1 is required in F2. So, X1 will go from F1 to F2. F3 does not require X1. So, I am not doing a flow from F1 to F3. Now, similarly, F2 solves for X2 and X2 is not required by F1, but X2 is required by F3. So, X2 flows from F2 to F3 and then F3 solves for X3. X3 is required in both F1 and F2. So, basically X3 flows from F3 to F1 and F2. Okay. So, in this way we can basically construct the graph corresponding to this occurrence matrix that I am having, right. Now, once I have the graph, I can do the Boolean matrix. That represents the flows from a vertex to vertex. From is along the rows, to is along the column as we had earlier. So, from F1 there is a flow to F2. From F2 there is a flow to F3 and from F3 there is a flow to F2 and also F1, right. Now, keep in mind that when I am solving this F1 for X1, basically, truly speaking, if F1 needs X1, where does it get from? It gets from F1 only, right. So, in addition to what the graph that we have, we also in fact have a self loop. The X1 that is required by the function F1, that is coming by the solution of the same function, right. Now, it may look complicated to begin with, but let us say the F1 contains something like x1 square minus x3 is equal to 0, and let us say I happen to solve it iteratively. So, now when I am solving it iteratively, I am basically looping over the same function in order to compute x1 in an iterative kind of a manner. So, basically for every variable that is the output element of a given equation, it basically forms a self loop on the same function as well, right. The same is true for F2 and same is true for F3, right? So, we can say that there is a self loop for every output element, and then for every other element we basically have a flow from somewhere else, basically whichever vertex is solving for that particular variable, right? What the self loop means here is that we also have a diagonal terms along the matrix. Now, if you look at the occurrence matrix for this case, we have something like the first row has F1 has x1, x3, and F2 has all 3, and F3 has x2, x3. You notice that the Boolean matrix happens to be basically a transpose of the occurrence matrix, right? So, as you can see here is a transpose of the occurrence matrix. Why is that? The reason is quite obvious, right? So, x1 is basically flowing out of f1 to every function like f1, f2 and so on. So, basically if we have to see the flows from f1, we have to look along the columns of this matrix, because f1 gives me x1 and x1 is flowing to everything which is along the columns corresponding to x1. Similarly, f2 is the output element of f2 gives output x2, and we have to look along the column, second column, to see where else x2 is going, right? So, basically along the column indicates the flows from a given function or a vertex, and if you look in the Boolean matrix, the flows from a vertex is along the rows. So, all the flows going from f1 is along the rows in the Boolean matrix, right, and along the columns in the occurrence matrix, and for that reason the Boolean matrix happens to be simply a transpose of the occurrence matrix, provided that we have a square occurrence matrix. If it is non-square, then it does not make sense to basically do the Boolean matrix, because Boolean matrix should be only defined when we have like a square occurrence matrix. Otherwise, you don't have a solvable system and you don't want to do it. Okay. Now, once we have this kind of a graph, then we can go ahead and apply whatever decomposition scheme that we have basically discussed in the previous lecture on this Boolean matrix that has come from this nonlinear system of equations, right? The first step, however, that we didn't have earlier in the linear system case is to delete essentially this self loops, right? So, what we do here is step 1. For decomposition, I am going to ignore the self loops, and that basically amounts to deletion of these edges x1, x2, x3 and corresponding elements in the Boolean matrix, which are essentially along the diagonal here. And now we go to our step that we followed in the decomposition. We look for the columns containing all zeros or the rows containing all zeros. In this case, there are no columns containing all zeros. That means there are no vertex without any ancestors. There are no rows containing all zeros. That means there is no vertex without any descendants. So, therefore, we go to our next step and we compute the R square and try to locate if we have a cyclical net of order 2. So, going there, so my R matrix is like this. So, my R square I will multiply the rows with column. The first row has second element as 1, second element is 1 in the third column, so I put a 1 there. Second row has third element as 1, third element is 1 in the first and second column, so I put 2 ones there. The third row and first and second element is as 1, first and second element is 1 in the second and third column, and now we locate that there is a cyclical net of order 2 formed by F2 and F3. So, F2, F3 is a cyclical net of order 2. And now we see, does it have any ancestors or any descendants? First we look at ancestors. So, we go back to the R matrix. So, F2 has an ancestor in F1. So, therefore, the F2, F3 has an ancestor. Now, we look at its descendant. So, F2 has a descendant in F3, but F3 has an ancestor in F1. So, although it is a cyclical net of order 2, we cannot essentially solve it first, because F2, F3 neither has no ancestors nor has no descendants. That is also pretty much clear from the graph. So, F2, F3 is forming indeed a cyclical net, as you can see here, but it has an ancestor in F1 and it also has a descendant in F1, right. So, in fact, if you look at it, F2, F3 is a cyclical net, but it is not maximal, because F1, F2, F3 is also a cyclical net. So, therefore, F1, F2 is a F2, F3 is a subset of F1, F2, F3. In order to convince ourselves, we can go ahead and compute R cube. And again we multiply the rows with columns, rows of R with columns of R square. So, first row, second element is 1, second element is 1 in R square in the first column and second column. So, we have 2 ones there. For second row in R, the third element is 1, third element is 1 in the second and third column of R square. Then the third row in R, the first and second element is 1, first or second element is 1 in all the 3 columns here. And now we see that there is a cyclical net of order 3 between F1, F2, F3, and since there is no other vertex in the graph, therefore, this cyclical net has to be maximal, and in this particular case we have to solve F1, F2, F3 simultaneously. So, now basically what we have been able to show is that whatever decomposition scheme that we have developed for the linear equation, this can be extended to any nonlinear system of equations. Again, we can do a Boolean matrix for the graph, and once we have the Boolean matrix, we can go ahead pretty much following the same kind of steps that we have followed, with only one extra step, that is, we have to ignore the self loops in the graph. Okay. So, let us consider one more example. So, we have here 4 equations in 4 variables, and we are asked to basically write first the equations and unknowns in the vector form. That is quite straightforward. So, x is x, y, z and m, and my function vector essentially is coming from the equations, but it is in the form f(x) equal to 0. So, we write it like following. And now we have to do the occurrence matrix for this case, that we can do by labeling the equations. Let me call them 1, 2, 3, 4. And now we have the equations along the rows and the variables along the columns. And now we have a square occurrence matrix. It's a solvable system. And the first equation contains all the variables. Second equation contains y, z and m. Third equation contains only x. The fourth equation contains x, y, z and m. So this is the occurrence matrix for this case, and now we should go ahead and do the order of precedence for solving this equation. But we have to be slightly careful here, because if I try to assign the output elements here, they are not along the diagonals. So first we have to make sure that they are along the diagonals. So in order to do that, we have some limitations. The third row only contains one element, that is my x. So x can be output element of 3. That is the only possibility here, because every row I have to assign one output element, and the third row contains only one element, so that has to be output element. For others, we have pretty much all the liberty that we want. So I can choose y from the first equation, choose z from the second one, and m from the last equations, right? So basically I am going to make 3 as the first row here, and then everything else will follow. So let me make 3 the first row. That will amount to numbering the equations again. So let me call this numbering 1, 2, 3 and 4. And now my occurrence matrix in the new numbered equations is going to look like this. The first equation contains x only. Second equations contain x, y, z, m. Third equation contains m, y, z, and the last equation contains x, y, m and z. And now the output elements can be along the diagonals. And now we can go ahead and do the Boolean matrix for this case, which is going to be the transpose of this matrix. So let's quickly do the Boolean matrix. So we have a transpose. So the first column here becomes the first row of the Boolean matrix. Second column becomes the second row. Third column becomes the third row, and fourth column becomes the fourth row here. And now I can do the graph for this. Now in order to decompose this, the first step is to ignore the self loops, and that means that we can basically delete the terms along the diagonal. So we ignore the self loops, and we can see we can now delete the diagonals here. And now we notice that basically the first column contains all zeros. So we can solve 1 first, and now we can delete therefore the first row and first column from the graph and also from the Boolean matrix. So let me delete the first row and the first column. And now I am left with this Boolean matrix. Again, now we see that there are no columns containing all zeros. There are no rows containing all zeros. So now I will go ahead and compute R square. So for first row, second and third element is 1. Second or third element is 1 in all the columns. The first or third element is 1 in the second row. So first or third element is 1 for all the columns. Then first or second element is 1 in the third row. that same is true for all the columns. So we get something like this. That already means that we are forming an order 2 cyclical net between 2, 3, 4 all together, and clearly none of them are having no ancestors or no descendants. Let's say I look at 2 and 3. 2 and 3 has an ancestor in 4. 3 and 4 has also an ancestor in 2, and 2 and 4 also has an ancestor in 3, right? So therefore we have to go ahead and compute R cube, which also is going to contain essentially all ones, and therefore we pretty much know that in this case we have to solve all the equations simultaneously, right? So we have to solve one first and then solve 2, 3, 4 simultaneously. Okay, so we can extend this idea and do other kinds of problem, and let's say we quickly do this particular problem. So in this case the occurrence matrix is given and we have to find the admissible output set along the diagonal by permutation. We can see if I want to put output elements along the diagonals, we are having a problem. We need to do some kind of permutation in order to put output elements along the diagonals, and in fact we can do that in 2 steps. First, we assign output element to every equation in a unique manner, so that all the columns contain only one output element and all the rows also contain only one output element. So you see here the shaded ones, they basically represent the output elements I have assigned, and it is done in a manner that each row contains only one output element and each column also contains only one output element. And now we basically do permutations here. So basically the third column becomes the first column in the new matrix. The second column remains same as earlier. The third column comes from x5. So basically my fifth column becomes the third column in the new matrix, and then my original fourth column becomes the fifth column in the new matrix, and the original first column becomes the fourth column in the new matrix. And after these permutations, we see that the ones are along the diagonals. Then we go ahead and we have the occurrence matrix, and we can do the graph for this case. Basically in this case, for the given occurrence matrix, we can transpose it and we can get the Boolean matrix. Once we have the Boolean matrix, we can do the graph. I will not draw the self loops. We do have a self loop for every vertex like 1, 2 and so on, but I will not draw the self loops. That amounts to essentially not considering the diagonal terms, because anyway we are going to ignore the self loops in the decomposition. So the graph is going to look like something like this. From 1 I can go to 7, from 2 I can go to 5 and 6, from 3 I can go to 1 and 7, from 4 I can go to 1, from 5 I cannot go anywhere, I deleted the diagonal term. From 6 I can go to 2 and 3, and from 7 I can go to also to 3. And this becomes the graph for this particular case, right? Now we can go ahead with the decomposition. The first step is deleting the self loops, that amounts to removing the diagonal terms in R. And once we have that, then we have the new reduced matrix after ignoring the self loops. And now once we ignore the self loops, we find that 4 is the column. The fourth column contains all zeros. That means we can solve 4 first, and once we have figured that out, we can delete the corresponding column and the corresponding rows from here. Now we have a new reduced matrix after deleting 4 from there, the fourth column from there, and now we see that all the columns are containing at least one, but the row for the vertex 5 is containing all zeros. So we can basically solve 5 last, basically following the same decomposition scheme. Once we have figured that out, we can delete the corresponding rows and column, and now we have the reduced matrix right here. And now we can see that there are no columns containing all zeros and there are no rows containing all zeros. So we move to the next step and we compute the R square. Once we compute the R square, we see 2, 3, 6 and 7. They are forming a cyclical net of order 2. So they are forming definitely in pairs because there are 4 vertices. And we see that if I look at 2 and 6, for this particular pair, the ancestors are only 2 and 6. So basically 2 and 6 is a cyclical net of order 2 with no ancestors, and therefore we can solve them simultaneously. So we can solve 2, 6 simultaneously. We already have figured that 4 we have to solve first, and we already have figured that 5 we have to solve last. So now we delete the corresponding rows and columns, and we can get a reduced matrix right here. We can compute its R square, and we basically end up getting 3 and 7 having a cyclical net of order 2, but 3 and 7 has an ancestor in 1. So therefore we need to go ahead, compute R cube. So we compute the R cube, and that means that 1, 3 and 7 forms a cyclical net of order 3. And now there is nothing remaining in the graph, so we have to solve these simultaneously. So now we have one step here, 1, 3, 7 has to be done simultaneously. So with that, I conclude this lecture. In the next lecture, we will take some more examples of nonlinear element decomposition, and then we can go ahead for other applications of graph theory. Thank you.